Hello, everyone, and welcome to today's exciting webinar. This is our first webinar in 2020, and we have at least 10 more webinars planned for 2020. I am Tim Stark, and I'm the host of today's exciting event. I am a professor of civil engineering at the University of Illinois at Urbana-Champaign and the technical director of the Fabricated Geomembrane Institute. Today's webinar, we welcome questions and comments which can be typed into your question box in the control panel. You may send in your questions at any time during the presentation, and our speaker will address them at the end of today's presentation. The recording of this webinar and a PDF of the slides will be available on the FGI website after today's presentation. A PDH certificate will be sent automatically to all who attend the entire webinar. Now, today's webinar speaker is Dr. Rudolph Bonaparte, who is board chairman at Geosyntec Consultants, Inc., headquartered in Atlanta, Georgia. He previously served as president and CEO of Geosyntec for 20 years, building the firm from a startup to 1,200 employees in more than 60 offices and in 6 countries. He is also a professor of the practice in the School of Civil and Environmental Engineering at the Georgia Institute of Technology. He is a member of the U.S. National Academy of Engineering, and today he will present his 2018 Carl Terzaghi lecture titled Geotechnical Stability of Waste Fills, Lessons Learned and Continuing Challenges. Rudy, thanks so much for squeezing this into your busy schedule, and the webinar is all yours.
Well, thank you very much, Tim, and I'm delighted to be here today to talk to everyone with the Fabricated Geomembrane Institute. I'm particularly happy to be part of this with Professor Stark. Our friendship goes back more than 35 years when we were young employees at Woodward Clyde Consultants, and our relationship has endured all that time. I'll also mention that Professor Stark has in many ways contributed to this lecture through the research he's done himself on the geotechnical stability of waste fills and the shear strength of municipal solid waste, and you'll see that at several points during my lecture today. Well, why is this topic important? The reason is that there are many thousands of waste fills in the US and many thousand more around the world. In the United States, for example, there are more than 2,000 active municipal solid waste landfills, thousands of closed landfills, and thousands of industrial impoundments of different stripes. And again, there are many more than that around the world. And the thing that we're interested in is their stability, because the instability of waste fills pose risks to lives, property, and the environment. And to illustrate that, I'm showing in the photograph here the OII Superfund site in Southern California that I've worked at in the past for many years. And what you're seeing here is a 250-foot high landfill containing hazardous wastes with a side slope on the order of 1.5 horizontal and 1 vertical. So a very, very steep slope sitting adjacent to the Pomona Freeway in Southern California high seismic zone. So just imagine if during an earthquake, this facility were to fail onto the freeway. So this illustrates why this topic is important, because of risks to lives, property, and the environment. Just as background, although I think everyone on this call probably understands the basics of landfills, I just want to cover a few things to make sure we're all starting off at the same point. What I'm showing here is just the anatomy of a typical landfill. We see the waste mass in the middle, and I'm indicating daily cover materials in the darker brown stripes. The waste is underlain by a composite liner system in this case, where the liner itself serves to prevent the infiltration of leachate from the landfill into the subsurface. And the leachate collection system, in this case a granular drainage layer above the liner, is used to convey leachate to a sump where it's pumped out of the facility for treatment. We see above the waste mass an intermediate cover soil, and I'm showing that because this will be important in several of the failures we talk about today, and then a final cover system and an active gas removal system. So this is the basic anatomy of a waste fill, or the type of waste fill we'll mostly be looking at today. And as it relates to geotechnical stability, geotechnical design engineers must be cognizant of multiple potential static and seismic failure modes that can exist at each stage of a waste fill development. And these include slip surfaces through the waste mass and along liner system interfaces, and through the waste mass and foundation of the facility. It also includes the stability of associated structures such as perimeter berms and stability berms, and veneer stability of the liner system itself or the cover system itself. We're not addressing veneer stability today. There's lots of information in the technical literature on that topic. We're only going to talk about stability that involves failure through the waste mass. So my lecture today is really a little bit of a story. It's a timeline with a beginning and an end. The beginning is the early 1980s to mid 1990s, when modern landfill engineering technology was first being developed and new regulations were being promulgated by the U.S. Environmental Protection Agency for both municipal and hazardous waste facilities. And this is when these facilities really started to be engineered, when liner systems were introduced to the facilities, and when they started getting very large because of the value of landfill airspace and the cost of building the facilities. And we'll look at, from this early period, a number of failures that occurred at that time and the things we learned from those failures. We'll then fast forward 20 to 30 years to what was, until January 1st of 2020, the current decade. But if I say the current decade, I mean the decade from 2010 to the end of 2019. And we'll look at a few additional failures. And we'll ask ourselves, why are we continuing to see additional failures after all the lessons that we learned during the earlier period? And I'll wrap up with a few observations and recommendations. So where we started in the early 1980s. During that time, there were a number of significant waste fill failures that drew the scrutiny of owners, regulators, and geotechnical engineers. And what I'll do is just briefly talk about three of these: Kettleman Hills, Crossroads, and Rumpke. Starting with Kettleman Hills, on the left-hand side in the photograph, we see an aerial view of the landfill cell. This is a hazardous waste landfill cell that failed after this photograph was taken. And what we see is a bowl-shaped cell with back slopes of 2 horizontal to 1 vertical to 3 horizontal to 1 vertical. The black materials are the liner system for the cell, and we see the waste mass prior to the failure in an interim filling configuration, and then the direction of movement of the waste mass when the failure actually occurred. On the right-hand side, we see the double composite liner system that underlaid this cell, and it had a lower composite liner consisting of compacted clay, low permeability compacted clay in brown, with a smooth high-density polyethylene geomembrane on top, then a second composite liner with a leakage detection layer in between, and a primary leachate collection and removal system above the top composite liner. So quite a sophisticated system, probably the most sophisticated liner system of its type at the time, 1988, when this facility was in operation. It was designed by a very reputable firm. And the question is, why did this state-of-the-art system fail? Well, to take a step back, in early 1988, a year after filling began, and with a waste fill in an interim configuration, and at a height of about 90 feet, about 600,000 cubic yards of material slid about 35 feet towards us, looking at the slide, over a relatively short period of several hours. We see in the photograph on the left an area of the back slope where the failure occurred after all the waste had been removed. So the geosynthetics and other components of the liner system are exposed. And we see here the torn geosynthetics, and what we're seeing is actually a geotextile layer that's sitting on top of the smooth geomembrane that we can't see because it's under the geotextile, and the tear in the liner system. So the forensic investigation revealed a translational sliding mechanism along liner system interfaces. Slippage was observed to be at the interface between the secondary HDPE geomembrane and the underlying secondary compacted clay liner. Post-failure testing that we conducted showed that this interface had very low strengths, undrained strengths, which we think are the applicable strengths for this interface at the time of failure, of only about 500 PSF for the residual sliding condition. So not much more than a soft clay in terms of an interface strength for this facility. The forensic investigation also revealed that the geosynthetic interfaces were very weak, with residual friction angles of below 10 degrees. Now, we knew before this that interface strengths were important to the design of these facilities. What folks didn't, for the most part, realize is how low the residual interface strengths could get. So that was one of the key lessons learned in this case. Analyses revealed some other things. I think in the interest of time, I'm going to pass over that point. We see in this slide some of the interface testing that was conducted as part of this forensic investigation. On the left-hand side, we see the secondary geotextile geomembrane interface, and in the right-hand side, the secondary compacted clay liner HDPE geomembrane interface. And the thing I want to point out on both sets of plots is the fact that peak interface strengths were developed at very low shear displacements, on the order of 0.1 to 0.2 inches of displacement. And then after the peak interface strengths were generated, there was a relatively rapid drop-off in strength to post-peak and eventually residual conditions. So as a lesson learned from this case study, this really jumped out, that these peak strengths for the interfaces can be generated with almost no movement at all, and that the strengths drop off relatively rapidly with additional shear deformation after peak. So some of the lessons learned from this case study: many liner system interfaces are weak and exhibit pronounced shear softening, as we saw on the previous slide, with residual strengths much lower than peak strengths. Liner system construction and waste placement operations can induce movements that mobilize peak interface conditions within the liner system, and thus the potential for progressive failure must be considered in design. We didn't understand that before Kettleman, that just the mere act of building the facility can induce deformations along liner system interfaces that could produce post-peak shear strength conditions. Waste mass stability evaluations need to address all interim waste filling configurations. This facility failed at an interim configuration, not a final configuration. When we're designing and looking at embankment dams, for example, we're usually not too concerned about stability during construction. It's after the dam is built and upon first filling of the reservoir. These facilities are different. Interim filling configurations can be most critical. We saw that the geomembrane CCL interface strengths are sensitive to their moisture, density, and shearing conditions. And this was an interesting finding because it created a bit of a conundrum. We know that CCL compaction conditions that favor low permeability and intimate contact between the geomembrane and clay to get a good composite liner action also favor low interface strengths. If we want low permeability, we want to compact the clay wet of the line of optimums with kneading compaction. Those are the very conditions that lead to low interface strengths. So as a design engineer, one needs to be cognizant of both of these factors when developing their specifications for the liner system. The second historical case study is Crossroads in Maine in 1989, and this is a waste mass and foundation soil failure. We're looking at the failed cell in the photograph here. You can see the direction of movement. The failure started on the right-hand side of this slide of the photograph, and it quickly migrated across the slide to the western or left-hand side of the photograph. This is an 8-acre landfill cell with a foundation consisting of very sensitive glacial marine clay silt that has an over-consolidated crust that transitions to a normally consolidated condition at a depth of about 15 to 20 feet. The clay silt layer served as an in-situ hydraulic barrier. There was no constructed liner or leachate collection system in this facility. And thus, one of the problems that this facility faced was the buildup of leachate within the landfill. So with the waste height at about 70 feet and after a period of heavy rain, a very rapid retrogressive slide occurred involving about 650,000 cubic yards of MSW. So a large amount of material, a very large slide that failed in a matter of only a minute. The sliding surface was found to be in the clay silt layer below the over-consolidated crust in the normally consolidated zone. And these waste blocks that we see with the grabens behind them were found to have moved from east to west approximately 150 feet across the site. At least the leading blocks moved that distance. So one gets the sense that this sensitive foundation soil liquefied and these blocks essentially rode on the foundation across the site. So this facility began operations about 10, 12 years before the failure. And over that time, the landfill owner filled the site and filled the site beyond the original limits such that they decided that just several months before the failure that they should do what they called updated stability analyses, considering the stage loading of these saturated, relatively soft, normally consolidated materials that were consolidating under the waste of the fill. And so they hired a geotechnical engineer to do the analyses, and those engineers came up with a factor of safety of about 1.0. At the same time, they installed inclinometers around the edge of the facility, as well as several piezometers, and they found that the foundation was shearing and moving at a rate of about 1.5 millimeters a month, which the engineers assessed as being high and acceptable. Now, you might think with this factor of safety in these movements, the owner would have stopped placing waste on top of this fill, but he couldn't because he had nowhere else to place it, and you'll see why in just a moment. So site operations continued, but some good things were done. The owner stopped placing waste around the rim at the crest of the facility and moved waste placement operations towards the middle of the cell. And interestingly and importantly, they placed stabilizing tow berms at the base of the facility on the east, north, and west sides, but not on the west side. Remember how the facility failed from the previous slide. It started on the west side. On the west side, not only was a berm not constructed, a stabilizing berm, but a 6-foot deep excavation was being made along the entire toe of the landfill for construction of a new line cell. So with a factor of safety of 1, not only was a stabilizing berm not constructed, but this excavation of the strongest material in the soil profile, the over-consolidated crust, was removed. This excavation led to localized overstressing at the toe, an initial localized toe failure, and then a rapid retrogressive slide. In fact, analyses that were conducted after the failure indicated that there was approximately a 14% reduction in the factor of safety as a result of this excavation at the toe. Now, this turned out to be kind of complicated because the forensic investigation showed that the degree of consolidation was poorly understood. which led to a misestimate of the soil strengths. They were estimated as being stronger than they actually were, but at the same time, there was a misestimate of the unit weights, and they were underestimated by about 25%. So it was actually a coincidence that they calculated the correct factor of safety, but did so using not quite accurate input parameters for shear strengths and unit weights. This slide shows an actual to-scale cross-section through the liner system with the pre-failure condition and the cut at the toe of the landfill into the over-consolidated crust, and then the relative locations of the failure blocks after the failure. This drawing was developed by Dick Reynolds, who we worked with for many years and Dick led the forensic investigations of the site after the failure. So some of the lessons here: both waste and foundation unit weights and shear strengths must be adequately characterized. Waste self-weight is by far the largest contributor to foundation loading, hence the importance of proper characterization. A clear understanding of the liquid levels and pore pressure conditions in the waste fill are critical to the satisfactory assessment of waste fill and stability. And each significant construction and/or operational change in the field should be evaluated prior to implementing the change. In this case, excavation at the toe triggered the slide. The toe excavation wasn't the root cause. The root cause was the overstressing of the foundation and the high liquid levels in the waste and the poor understanding of the actual unit weights and strengths. But the excavation at the toe was the straw that broke the camel's back. And finally, for soft soil sites, the rate of waste filling may need to be limited by the rate of foundation soil consolidation and strength gain. This is a classic stage geotechnical construction condition that must be thoroughly understood. And for any kind of geotechnical structure on a soft foundation, we need to be concerned with foundation consolidation and the acceptable rate of load application, whether it's a landfill, a highway embankment, an embankment, a dam, retaining wall, or another structure. The last historical case study, and one that Tim Stark knows very, very well through the good work he did on behalf of the Ohio EPA, is the Rumpke facility in 1996 in Ohio. And this is a waste mass and foundation soil failure. And we see here the existing landfill. It was a large facility in 1996. And we see the area of the failure, and it's below this yellow dotted line, which is the original toe of the landfill. And the area that failed is about 8 acres in size, and it basically slid from south to north in the directions shown. And it slid a very long distance, in part because underneath this failed waste was an excavation for a new lined cell that was not ready for filling. And this will be one of the factors that is causative in this failure. Not the fact that the excavation was there, but the fact that the new line cell wasn't ready for filling at the time of the failure. The excavation itself didn't contribute to the failure, but due to the depth of the excavation, the kinetic energy of this failing mass was increased by the deep excavation and allowed the material to move quite a long distance. So the story of Rumpke starts in the 1940s when waste was placed in ravines on the property directly onto clay, colluvial, and residual soils that formed a mantle over bedrock. And I've highlighted that material because, as Professor Starkwell knows, that's one of the main actors in this tale. And landfill continued until 1996 to a point where the grades for this landfill exceeded the permitted design grades. And I've highlighted that because it's an important fact as well. About a week prior to the failure, tension cracks were observed at the top of the landfill at the eventual location of the headscarp we see here. The morning of the slide, the toe of the landfill began to move, and the tension cracks at the crest were observed to be growing wider. After several hours of gradually increasing creep rates, as this waste mass continued to move over several hours, the slope failed, starting at the toe area and retrogressing to the headscarp location. In only about 5 minutes, 1.5 million cubic yards of material slid hundreds of feet into the adjacent excavation. So this was a very large slide, perhaps the largest in modern US landfill engineering history. So this is a figure from an ASCE paper authored by Tim Stark and his colleagues. I've modified it a little bit to make it a touch more artistic for this presentation. And as I mentioned earlier, due to delays in opening the lateral expansion, this excavation here, the landfill top deck had been overfilled by about 30 to 40 feet in the 18 months prior to failure. And we see this overfill, the darker brown material, and to a steeper slope, which we see here, than the permitted design, up to about 2.6 horizontal to 1 vertical, compared to the slope for the permitted landfill of 3 to 1. No, to the best of our knowledge, no stability analyses were conducted to evaluate the behavior of this overfill or the influence of this overfill on the stability of the landfill. The forensic investigation showed that the slip surface extended at a near vertical angle from the landfill crest at the location of the headscarp from the previous slide through the waste to the native soil, where it followed the bedding layer right along the native soil layer as we see here. The investigation determined that leachate heads in the waste mass at failure were substantial, on the order of 30 to 40 feet in locations. So there were significant hydraulic pressures acting in the fill at the time of failure. Post-failure shear testing of the native soil, conducted both by Geosyntec and by Professor Stark at the University of Illinois, produced fully softened and residual friction angles in the range of 20 and 8 degrees respectively. They varied a little bit. These are average values. And we can compare that to the average mobilized friction angle at failure based on back analyses. And again, it varied by cross-section, and it varied depending whether you're doing a 2D or 3D analysis. But a good average value for this story is about 12 degrees. So we can see that at failure, the strength along the native soil layer was below its fully softened value and a little bit above its residual value. An excavation at the toe for an access road and freezing conditions that impeded leachate drainage at the toe may have contributed to the initial triggering of the slide. But as I said, for the last case study, neither of those things were really the root causes. They were, again, perhaps the straw that broke the camel's back and caused the failure to occur on the day it occurred. But the overriding considerations, the overriding root causes were the low strength of the native brown soil, the overfilling of the facility, and the high leachate levels in the facility. So some of the lessons learned here: foundation conditions for old unlined waste fills must be thoroughly understood if additional filling, excavation, or expansion of the fill is planned. Strain incompatibility between MSW, which is ductile, and colluvial soil, which is brittle, can lead to an even development of shear resistances, localized shear softening, and progressive failure. So we incorporate that today in our design approaches. We didn't so well back in the day. And leachate buildup in old unlined waste fills can reduce slope stability factors of safety and contribute to the development of unstable slope conditions. They need to be assessed if one is going to continue to place waste in these older fills. And we need to be cognizant that operational activities, i.e. in this case, filling above the permitted grades, may reduce slope stability. So by the mid-1990s, we had learned a lot. And some of the key lessons learned are presented here. Most importantly, don't forget fundamental soil mechanics. Waste materials have geotechnical properties that must be characterized. Just like we characterize soil materials, we need to characterize waste materials. Liquid and gas conditions in the fill are important. They can create elevated pore pressures. Soil and geosynthetic interface strengths must be characterized, both peak and residual or large displacement. Mobilized strength compatibility is often an issue because waste is ductile and other parts of the system tend to be fairly brittle. As a consequence, progressive failure mechanisms must often be considered. Time-dependent staged loading response must be addressed at soft soil sites. Numerous interim waste configurations often require assessment. Operating conditions in the field often deviate from the original designs. You know, you might design something that has an operating life of 15 or 20 years, and things change during that period. Approach expansions on top of old unlined landfills with caution. We saw that at Rumpke. Surface cracking and toe bulging may be signs of incipient failure. And communications between the engineers and operators are critical, not only at the beginning, but through this 10 or 15 or 20 year operating life. So by the mid-1990s, we had learned a lot. In fact, in a paper in 1995, made the bold statement that I thought we had learned enough to say that we knew how to design these types of facilities to both be environmentally protective and structurally stable. And that was perhaps a bit too optimistic on my part. So let's go on and look at the current decade, 2010 to 2019. And while I call this continuing challenges, I could just as easily call this part of the presentation. So why do we keep having these waste fill failures? I think you see where I'm going. So fill stability failures have continued to be an issue during the current decade, and there have been more than one per year on average in the United States. And a partial list of those facilities are given here. A number of them are listed as confidential at the request of the owner. These are facilities where we were part of the forensic investigation, so we have information about the failure, but we need to keep the site confidential. And I suspect there are other sites where other engineers may have been involved in the forensic investigation where they're keeping the information confidential. So there may be facilities in addition to these facilities that would make up the total population. I'm just going to talk about three that are all interesting in their own right, and we can see the lessons we learned at these three facilities. This first facility, the failure occurred in 2011. It's located in the eastern US, and it's a waste mass and intermediate cover soil interface failure. We see the failure area here. This is well, I'll explain what happened in a second. This is the toe of the landfill I'm showing right here. And you can see that the waste ran out a distance of about 500 feet beyond the toe. And this is a relatively flat site, so you get a sense that the material in this area liquefied, and as it liquefied, it flowed quite a distance beyond the toe of the landfill. We're seeing an area after it's been cleaned up, this road's been reinstated, some of the waste has been moved around. So at the time of the failure in September 2011, waste filling had recently been completed and a landfill expansion being built over the 190-foot tall slope of a previously filled landfill. So think of a landfill, if you can, you can see me. We have an existing landfill like this, and the owner wanted to create additional airspace, so they extended the liner system out another 100 feet beyond the limit of the landfill and filled a veneer up that 190 feet. And that veneer of waste was placed on the intermediate cover soil of the original landfill. And so that veneer exists all along the slope here. And only a portion of that veneer failed in the failure. This was a very wet landfill. It practiced leachate recirculation, and it had been recirculating liquids for a number of years. So that helped to create a relatively wet landfill. In addition, the stormwater management practices weren't perhaps as good as they could have been, and that resulted in significant amounts of stormwater infiltration into the facility. And finally, the facility accepted dewatered sewage sludge. And while it's dewatered sludge, the sludge is still wetter than the moisture content of typical municipal solid waste. So all these things help to make this a relatively wet fill. Failure occurred in the expansion area in this veneer in a matter of minutes and involved about 160,000 cubic yards of waste that flowed about 500 feet beyond the limit of the liner system and retrogressed, as we see on the top, about 100 feet beyond the crest of the facility. This is after more cleanup of the site had been done. And here you see the intermediate cover soil layer upon which waste slid down the slope. The post-failure investigations showed that the slip surface was at the interface between the expansion area and the underlying intermediate cover soil layer. CPTU testing, about 20 soundings, were advanced in unfailed areas under a very strict safety program, I might add, but in unfailed areas around the perimeter of the waste. And from that, we were able to ascertain that piezometric levels in these slopes were quite high in the areas that hadn't failed, and by extension in the area that had failed prior to the failure. On-site observations the day after the slide revealed leachate pools and gas vents within the failure area, clear evidence of a wet, pressurized fill. And I should add that the operator, who was trying to do their best, struggled with keeping the gas extraction system going in this portion of the facility. So if you think about it, a very wet facility, high degree of saturation, would have very low gas permeability. You're not able to extract the gas because the system isn't operating well. You're getting gas pressure building up within the unit. And that's what we think was happening here. Here's a cross section through this facility at the area that failed. We see the original landfill with the liner system below it, the 100-foot extension of the liner system, and then the veneer fill that was created fairly quickly over a period of about 18 months. And the intermediate cover soil that, in essence, served as a leaky liner beneath this expansion area, such that the piezometric level built up in this area over time and couldn't drain out into the original waste mass and down to the bottom of the cell. And here is the morphology of the failure mass in gray after the failure, and you can see the large runout distance of the material. So you really get a sense of how the waste liquefied. Slope stability analyses were conducted using the CPT-derived piezometric levels in the observed failure surface. And we see the results of the analyses here, and you can see how the failure came out about mid-slope. Back analyses of the failure resulted in a drain waste friction angle based on 2D limit equilibrium analyses of 26 degrees. At the same time, we obtained some samples, obviously disturbed samples, and we sent them to Ed Kavazanjian at Arizona State University to test in his 18-inch diameter direct shear box. We estimate that the samples were about 75% municipal solid waste and 25% sludge. These tests resulted in drain secant friction angles of 24 and 20 degrees respectively at 10 and 20 psi. So you see the normal stress dependency of shear strength here, and you can see that they're a little bit lower than the back calculated strength, which isn't surprising because they're disturbed samples, and in a direct shear test, you're testing along a horizontal plane, which is the weaker plane in the waist. Nonetheless, taking these results together, we think they show that the waist in the slope was weaker to a degree than it might be for typical MSW, such as the strength relationship developed by Ed Cabazanjian and myself in 1995, and more recent relationship that Professor Stark and his colleagues have developed for municipal solid waste unit weight. So this is possibly an indicator of the effect of the sludge on the shear strength of the waste mass. So some lessons from this case study: excessive leachate recirculation and stormwater infiltration can lead to the buildup of elevated liquid levels and pore pressures in the waste, as we saw. Vertical expansions that involve the placement of new waste over old need to account for the interface conditions. In this case, a low permeability intermediate cover impeded leachate percolation from the expansion area to the leachate collection system at the bottom of the original landfill, contributing to leachate buildup. Either that cover needed to be removed or ripped up such that it was permeable, or a new leachate and collection and removal system needed to be placed on top of the intermediate cover soil layer to drain the veneer. And gas collection efficiency can be greatly reduced in excessively wet landfills. This is just like saturated soils. We know when unsaturated soils, we know when the degree of saturation in an unsaturated soil goes up, its gas permeability goes down. And the same thing is true in a waste mass. So as the moisture content in the waste mass goes up, the gas permeability goes down, and it gets harder and harder to get gas out of the fill. And finally, the effects of sludge on the strength, permeability, and degree of saturation of the waste mass must be accounted for in design. So some very important lessons learned that are for the most part a little bit different than the lessons we learned earlier. Second case study is really quite interesting as well. This is in the southern US. It occurred in 2012 and is another waste mass and foundation failure. And we see the slope that failed here. You almost get a sense, you see the graben and the back slope to the failure area. You almost get a sense, seeing how intact that this slope is, that this failure area translated from east to west some distance, and it's not a rotational failure. You don't see any distress in the body of the slope itself. So I'll ask everyone here who's a geotechnical engineer to put your soil mechanics fundamentals hat on, so to speak. This landfill cell was constructed in a deep excavation, about 45 to 60 feet deep, into over-consolidated native clay. This whole area here has been excavated. This area was excavated in advance of needing it for landfill disposal to create borrow soils for landfill construction, berm construction, and other things. Now, the excavation occurred in 1996 to obtain borrow soil for ongoing site operations. But liner system construction in this excavation did not begin until 2007. So for more than a decade, this deep excavation into over-consolidated native clay stood open and stormwater ponded at the bottom of the cell. There was a liner system beneath the cell. I'm not going to go into it because it was not involved in the failure. After the liner system was constructed, waste filling occurred from mid-2007 to early 2009, creating the slope we see here, about 95 feet high, with an inclination of 4 horizontal to 1 vertical. And for those of you involved in the design of these facilities, you're going to say, that's neither a very high nor a very steep slope. So why did it fail? The failure involved translational movement in February 2012 over a several-day failure period. So this was not a rapid failure. This was more like a creeping failure. Of note, the failure occurred 3 years after filling was substantially complete and after 3.5 inches of rain fell in the preceding 48 hours. This aerial view shows the failure area. This is east at the top. We see the Graben and the headscarp area from that we saw in the previous slide. For scale, this is about 3 football fields in length. And the sliding occurred in this direction. Here's the other edge of the cell. And we can see here bulging at the toe of the cell that failed. So this whole area moved in this direction. The first signs of a problem occurred 3 months prior to the failure when north-south oriented cracks occurred at the eventual location of the slide headscarp. Well, what do people do when they see cracks in their slopes? Often they refill the cracks and they smooth out the ground and reseed it so it looks good and they make the crack go away. But the cracks reopened, and typically after heavy rain events. So this was a sign that this slope was already starting to move. The slide itself involved translational movement, about 700,000 cubic yards of waste and soil, a distance of about 25 feet over several days, as I said. For additional scale, you can see some large compactor equipment down here. It gives you a sense of the scale of the slide. The forensic investigation concluded that failure mechanism involved shallow translational movement of the native clay beneath the bottom liner system, but probably only within 5 to 7 or 8 feet of the bottom liner system. Unfortunately, we were not able to install piezometers and instrumentation at the site until some time after the failure occurred. It was a matter of several months, and the owner preferred that we not install piezometers within the footprint of the waste mass. So we didn't have good piezometric data for the pore pressure conditions beneath the fill. For a variety of reasons I won't go into, we thought they probably weren't very much different at this point in time from hydrostatic conditions, taking from the location of the failure to the leachate collection and removal system in the liner. So we did get good soil samples and did a large amount of laboratory testing, including torsional ring shear testing, direct shear testing, and triaxial testing. And on the left-hand side, we see some results for weathered and unweathered fat clay material in a torsional ring shear test. And these are residual strength values we see here. And from those, we came up with a residual friction angle of 6.7 degrees with a very small cohesion for use in our stability analyses that best represented the normal stresses of interest. We also came up with a fully softened shear strength value of about 13.1 degrees. And I'll mention here that these residual and fully softened shear strength values correlate relatively well with the correlations that have been developed by by Professor Stark and his colleagues based on the liquid limits and percent clay fractions of the materials that he's published, authored and been published in the ASC Geotechnical Journal. So without good pore pressure data, we approached our slope stability analyses in a two-step process. First, we reasoned that after 25 feet of movement, the post-failure configuration of the waste mass would correspond to residual shear strength along the slip surface. There was a lot of shearing, and the strengths along the slip surface would have dropped to residual values. We also knew that the factor of safety at the time of failure had to be about 1.0. So with that information, the geometry, the shear strength, and the factor safety, we were able to back calculate an average pore pressure coefficient 0.14. And this is fairly low, but remember the R sub U is calculated based on the total vertical stress acting at the depth of the failure. And this, while it's a relatively low pore pressure coefficient, it actually corresponds fairly closely to hydrostatic conditions between the elevation of the failure and the drainage layer in the liner system. So we had, from multiple lines of evidence, some sense that this wasn't a crazy number to use. We then took the pre-failure geometry of the slope, which we had, the same pore pressure coefficient, and we calculated an operative strength for the waste at an early stage of the failure prior to it having very much movement. And we calculated a friction angle of 10.6 degrees. So significantly more than the residual strength value, but less than the fully softened strength value. So putting this all together, we think the story for this facility is that the decade-long open excavation allowed ponded water to infiltrate the native clay through desiccation cracks, slickened sides, and soil suction. This led to swelling and softening of the clay and fully softened shear strength conditions. And again, for the geotechnical engineers on this call, do you remember, I think it was a 1957 paper by Alex Skempton in the journal Geotechnical, first time slides in London clay, or a title along those lines, where he talked about precisely this mechanism in the highly over-consolidated London clays that were, through which deep cuts were being made for the British motorway system. Exactly the same mechanism. And so with that softened material, then as the cell was filled, the shear stresses generated by the waste fill induced shear deformations in the native clay that drove the shear strength to a value lower than the fully softened strength. And when it was driven by shear deformations to a value on the order of the red line we see here, the slope gave way and it moved 25 feet, and ultimately we have shear strength corresponding to the residual value on the slip surface. So this wrap-up slide for this case history shows the slope after the movements. You can see the movement in the headscarp area here and prior to the movement. So these are the two sets of analyses that we did. And the lesson here is really pretty simple, just one. Geotechnical fundamentals matter. Same lesson we learned earlier. And in this case, the over-consolidated plastic clay, a lack of real consideration of how that might respond to the excavation was the root cause of the failure. We're almost to the end here. This is the last case study. This is in the Northeast US in 2017, and this is a waste mass failure. We see the felled area here. It's about 15 acres. You see a truck cab here in the center of the failure area, which gives you a sense of the scale of this failure. So in February 2017, a 15-acre waste slope failure occurred, sadly resulting in one worker fatality. In the weeks leading up to the failure, surface cracking, slope bulging, leachate seeps, and gas venting were all observed at the site. At the time of the failure, the owner was trying to do everything they could to relieve the conditions that they believed were developing in the cell. And one of the principal things they attempted to do was to install a series of gas wells. But the contractor struggled to get those wells in, and there wasn't enough time. But the owner was doing what they could. The failure occurred over about 10 minutes, starting with the bursting of the bulging landfill face, which triggered a larger slide, releasing about 220,000 cubic yards of waste. that flowed up to several hundred feet beyond the limit of the liner system. And we see that failure here. Here's the face of the cell that bulged. In fact, there's two faces, and there's like a 90-degree angle right here. So it bulged in this direction and failed in this direction, and it bulged in this direction and failed like this. And you can see the run out at both locations. And this is the limit of the disturbed area. The area where the failure occurred involved an expansion of a new waste cell against the intermediate slope cover of an older portion. And it really wasn't an expansion, it was the next cell in the landfill's development, but like the earlier expansion, it involved placement of waste on the intermediate cover slope of the previous cell. So again, in a sense, you have this veneer configuration, although the veneer in this case was much wider. The intermediate cover for the original landfill consisted of cuttings from oil and gas drilling operations blended with lime, and this created a relatively hard, smooth, and impermeable layer upon which the waste was placed. So again, like the previous case study, there was no removal of the layer or installation of a new leachate collection system on top of the layer. In addition to the MSW, the landfill accepted a variety of special wastes, including sludge, which we're terming low shear strength waste, or LSSW. We see here a drawing of the site and a whole bunch of cone penetrometer tests that were performed. And the brown areas show zones where the landfill, the waste mass, had the highest concentrations or the highest percentages of this low shear strength material. And you see there's relatively less near the face of the slope and higher concentrations in the back. And that came out of some operating procedures that were very well intentioned. So the operations plan called for the landfill to place the low shear strength waste back at least 100 feet from the slope of the fill to prevent leachate seeps and to maintain stability. Now, this is a good idea. The setback, though, limited the cell area in which the LSSW could be placed and the amount of MSW available for mixing with the LSSW. And that's because this cell had a 90-degree angle. So if you chop off this whole 100-foot, veneer along the slope and don't have, and that's only municipal solid waste, you're pushing your disposal of LSSW back into this area. And then in addition, the MSW was being used up to create these berms, if you will, these non-LSSW areas. So you didn't have enough MSW to mix back here. So this resulted in an interior zone in the cell, the brown, with higher proportions of low shear strength waste, which was an unintended consequence of good ideas, or what were thought to be good ideas, and ultimately a weak zone for which the shearing occurred. So while the landfill only accepted about 20% LSSW by total tonnage, these operational factors resulted in zones estimated to have up to 40% LSSW. And why is that important? Well, we see here in the middle representative samples of MSW and LSSW, and you can immediately see the difference in consistency. So representative samples of these materials were obtained from the site, and they were sent to Colorado State University to Chris Barether and Joe Scalia for direct shear testing in Craig Benson's 12-inch diameter direct shear box. And the testing was done on the materials alone and then different percentages of each material. And the test results showed that the MSW LSSW mixtures became substantially weaker at LSSW mass fractions about 40%. In fact, I'm surprised they didn't become substantially weaker at about 25%, which is where I normally think of there being significant impacts of special waste on the waste mass. And what we see here are the test results for the different percentages of LSSW by weight. And you can see that at low LSSW fractions, the strains correspond to those of MSW for the most part. And then as you have increasing LSSW contents, the strains decrease and decrease and become very weak for pure LSSW. So the lessons here: special non-MSW wastes can create operational problems. Procedures developed to mitigate the problems can have unintended consequences. Special wastes, if placed at too high a mass fraction, if not thoroughly mixed with MSW or other stronger material, will create weak zones that adversely affect waste stability. And low permeability zones in the waste, either from the special wastes themselves, i.e. a saturated sludge has low permeability, or trapped liquids and gases due to cover soil layers and other things can cause the buildup of elevated fluid pressures. So to wrap up, observations and recommendations in light of continuing challenges. The first thing is we're relearning many of the lessons first learned 25 years ago. And the answer is why? Why are we relearning today lessons that were learned a long time ago? Is it the fate of humanity that every generation has to relearn things for themselves? Every generation of engineers has to relearn lessons from the previous generation. Are we in a time period of information overload, or are there other factors? But really something to think about. More recent lessons learned: first, aggressive leachate recirculation can saturate waste and cause high piezometric levels. As a friend in the industry once said with respect to leachate recirculation, it's like having a drink of alcohol. If you drink, you need to drink responsibly. And the same thing applies with respect to leachate recirculation. Gas well collection efficiency is substantially diminished in very wet landfills for the reasons we've already talked about. High moisture content landfills can lead to elevated temperatures in some cases. I didn't talk about that in the lecture, but that's a significant matter in our profession today. Co-disposal of sludges and special waste can lead to stability and other problems, and we saw that in several examples. And vertical expansion configurations and materials have contributed to waste failures. And so, what can we do about that? Well, some recommendations. Leachate recirculation rates may need to be moderated to avoid saturating the fill. A proper water balance should be maintained in the waste fill, and this would require monitoring at recirculation landfills. And additional internal drainage features such as chimney and trench drains may be needed to drain the fill. Sludges and special wastes. I advocate for detailed special waste acceptance plans, and they should be developed for each special waste stream. These swaps, if you will, should address potential impacts to leachating gas generation rates, waste properties, slope stability, and operations. We need to think carefully about unintended consequences. We saw the efforts of that last case study to do things the right way and how it had some unintended consequences. And a higher level of operating vigilance is needed when we're disposing of special wastes. This is the classical observational approach. And then lastly, vertical expansions. The intermediate cover interface must be carefully engineered for stability and permeability. In some cases, the cover should be removed. In others, a new LCRS should be placed or installed on the top. And the effects of the vertical expansion on leachating gas movements in the waste fill should be carefully assessed. I'll mention that all of this is, I've submitted a paper writing up this case study to the ASCE Geotechnical Journal, and I'm hoping it will be published in the not too distant future. So all of this information will be available to you. I'm going to skip this one slide and come to the end and just say thank you very much. I know I've gone a little bit over schedule. Tim, I'll turn it back to you.
Great, Rudy. Thank you so much. We have some questions I'd like to go through. there are a number. I'm not sure we're going to get through all of them, but let me start. A number of your cases involved interim slopes and versus final slopes. And the question is, regulations in some states, including Ohio, have included consideration of phasing plans, interim slopes, etc. Is that helpful, or is that creating a false sense of comprehensive engineering?
I think it probably depends on how faithfully the owner follows the phasing plans that were investigated, for which slope stability studies were conducted during design. And if they are followed faithfully, then I think that's a good thing. If they're not, and the phasing is changed quite a bit during operations, then the value of doing those analyses as part of the design would go down. And, so I think what would be helpful would be is if regulations or no regulations, if everybody, so to speak, in the supply chain of landfill development, from the owner to the engineers to the operators to inspectors, understood that if there is a change in the phasing during the life of the landfill, there is indeed a need to reevaluate interim slope stability. And I think in some cases that may be the missing step. But
Yeah.
and I do, Tim, just to finish, I do advocate for conducting phasing slope stability analyses as part of the original design.
Right. Yeah, and of course, a lot of regulations just speak to the final slopes, which leave out the important interim. Rudy, here's another. Back in the 1990s, bioreactors and leachate circulation were coming into play and being used a lot. It's a long question, so I'm going to kind of summarize it. The liquid, it was assumed it wouldn't result in long-term moisture increases to the waste mass, and it wouldn't end up in the leachate collection system. I've seen a wide range of recirculation rates that are supposed to match up with the degradation process. Has the science of what we know about recirculation changed, or are there bad effects strictly due to recirculation at high rates?
Yeah, great question. Probably could be a whole lecture unto itself that you may be able to give better than me. But we are seeing cases of large landfills without adequate internal drainage, for which the waste mass is not draining at a rate that is leading to maintaining the waste mass at a level of saturation that doesn't impede gas removal efficiency of gas wells and potentially lead to other problems such as seeps and other kinds of conditions. And I think the question of, is too much liquid being put into a specific landfill can't be answered in a vacuum. I think it's got to be comprehensively evaluated in terms of what the starting moisture contents are, how good the internal drainage systems are, and what types of daily and intermediate covers are using, and whether they're creating impedances to the drainage of the material in the facility. And all of those go into the response of the holistic response of the facility to this recirculation activity. And one needs to understand all of them to really get it right. If you have, for example, a number of chimney drains connected to trench drains, which is relatively uncommon, but not completely uncommon, you can do more with recirculation than if you don't have those features and you have low permeability daily and intermediate cover soils throughout. So I think all of those things need to be considered together.
Yep. Another related question to leachate recirculation: how do we control the leachate recirculation rate? Is it waste related, environmental condition related? like temperature, rainfall, or related to cover liner parameters?
Yeah, I think it's all those things, as I just said. I mean, my response would be it's all the same things. You need to think about the type of waste you dispose, the type of cover material you're using, whether your design includes internal drainage features, the height of the facility, the size of the facility. We're seeing more and more for very large landfills, 200 feet high and higher. The level of compaction of the waste at the bottom of the facility is such that it becomes a lower and lower permeability material, even in the absence of low permeability daily cover. So all of those things need to be considered in concert when evaluating your strategy for leachate recirculation.
Yep. Another question, I think this relates to one of your Eastern US case histories that you covered at the end. Should you have used prefabricated vertical drains or wick drains and pre-consolidation loading on the area prior to constructing the new cell?
So this must be for the southern U.S. facility.
Oh, sorry. Okay.
Yeah. In this particular, if it had been a normally consolidated soft soil, I would say the answer is yes. Although in this particular case, the owner would have had concerns because they had a clay liner without a geomembrane, and because of the thickness of the clay, it was hundreds of feet, they were using a natural attenuation, the natural attenuation variance or alternative in EPA regulations for their liner system. So without putting a geomembrane in, they probably couldn't have used wick drains. But if it had been a normally consolidated site, but remember, this was a highly over-consolidated, slick-sided, fissured material that once it's softened, wick drains or no, the failure was preordained. This was not an excess pore water pressure problem for this failure. In fact, in the area, in the zone that failed, I didn't mention it, but we estimate that the degree of consolidation was probably 80 or 90%. This was a problem of, this was a classic over-consolidated clay softening failure.
Yeah, yeah. A follow-up on one of the leachate recirculation questions. Recirculation isn't intended to result in liquid ending up in the leachate collection and removal system. The only benefit is to enhance methanogenic bacteria. Are we rethinking the benefit of adding extra liquids to the methanogenic bacteria?
Well, if you put it in, most recirculation projects I've seen, some of the liquid does get to the leachate collection and removal system. So that, I think that's just a practical reality. I am not negative about leachate recirculation and enhanced biodegradation of the waste. I think that we just need to do it in a way that incorporates, the lessons learned that have been presented here and other lessons learned. So it's done well and it's done in a way that doesn't lead to problems that in some cases can be quite significant to correct.
Yep. And you touched on it earlier, making sure that there's no adverse reactions with the recirculation as well, in addition to stability. Okay, let me see. Okay. Here's one from me.
Uh-oh.
Be the last one. It's just softball. So there's an interest now in three-dimensional slope stability analyses where we generate some extra resistance along the sides of the slide mass. but still only using two-dimensional factors of safety. Any thoughts looking forward to waste stability so you don't give this lecture in 5 or 10 years and with more problems? Any thoughts about 2D versus 3D slope stability analysis?
Yeah, I think using 3D slope stability analyses can give you a better understanding of the failure mechanics than in many cases a 2D slope stability analysis can do, and particularly in certain situations. For example, the Kettleman Hills is the classical example of that. For practicing engineers, it's a challenge because for the most part, we're not all that conversant in it. And oftentimes there's neither time in the schedule nor a level of funding from the client to go into that level of inquiry. So unfortunately, I see a gap between, the kinds of studies that can be performed in a university setting, or for the most studied projects, but will not be used maybe for other projects that are a little more common. And so I'm not sure how much it's going to become, say, a standard of practice in the industry. And I think one of the challenges we have when we look at some of these sites is figuring out the appropriate, where to cut the appropriate 2D sections to give us the most representative results. And I think all I can recommend in that regard is that, out of being prudent, it behooves us when investigating these kinds of things, and even when conducting analyses for new facilities, to make sure that we're cutting enough 2D sections that we at least get alerted to whether we're seeing the kinds of changes in factors of safety between sections that might indicate to us that 3D effects could be important.
Yep. Couple more questions are rolling in. Have you been involved in any zone of influence / run out analyses for landfill failures? In other words, I think they're asking, is there a typical way to estimate the run out zone?
Yeah, I'm not familiar with any. The programs for that kind of analysis exist for mine tailings materials, where for years people have investigated those types of things. And there are some new techniques being developed for very large deformation kinds of problems. Tim, you know the name, it's escaping me right now, the point.
Material point method.
The material point method that have promise. I think the challenge in applying them to a municipal waste landfill by far is going to be the material property characterization and an understanding of the liquid and gas pressures in the facility. We just don't, I think, perhaps know in many cases the characteristics of the material well enough that conducting that kind of exercise would give you results that you could really have confidence in.
Yeah. Here's a real difficult one. Analyses provided appear to utilize effective stress shear strength parameters. When is it appropriate to use an effective stress cohesion? And I assume they're referring to the waste versus an interface, but I'll let you handle it.
Well, I think whether you use just a friction angle or a friction angle and a small cohesion, the important thing is to make sure that the failure envelope you use generates the right shearing resistances in the normal stress range of interest. And so I think that's the first thing to keep in mind. And generally, my feeling is that for municipal solid waste, cohesions should be fairly small. We know that there's interlocking of waste. We know you can characterize it by a cohesion, but I think where you have pressures and poor pressures and you're trying to model those things, you may be better off principally relying on the frictional characterization of material and making sure you have that, you know, as appropriate for the normal stresses of interest.
Yep. Okay, I think that covers most of the questions, and we're a little over time. So let me wrap up. The PDF will have a slide that has, oh, there it is, Rudy's contact information. If you have any additional questions, you can email Rudy directly at rbonaparte@geosyntec.com. Next slide introduces the fabricated, or the next webinar that we're planning for the Fabricated Geomembrane Institute on floating cover systems for reservoirs and ponds by Graham Fairhead of FabTech in Australia. And so I want to encourage everybody to check out the FGI website as well as the IGSNA, the International Geosynthetic Society North American chapter websites, to learn more about these organizations and learn more about geosynthetics and how to use them in civil engineering applications. So with that, Rudy, thanks again so much for squeezing this into your busy schedule and joining us from Atlanta, Georgia.
Thank you very much, Professor Stark. I enjoyed it.
Great. Thank you, and thanks to everybody for attending.
Bye-bye.
Bye.